All right, let's get started. Welcome to the HPRC short course, Transition State Search and Advanced Topics with quantum chemistry simulation using ORCA. My name is Xin. I'm your instructor for the afternoon session as well. If you have participated, if you have attended the morning session, or if you've already used ORCA before, you're very welcome to learn more about transition state search and calculate something called kinetic isotope effect. So this afternoon session is like hands-on intensive. We just put more emphasis on the hands-on part. So for some of the hands-on part, I'll give you a live demonstration. This is the agenda for the afternoon part. We will have 3 short lectures that will be talk about the basic concepts of potential energy surface, what is a transition state, and how to what is kinetic isotope effect and how to calculate that. And then the 3 hands-on part, just to give you the real practice on how to find transition state with like the OPTTS methods in ORCA and the NEBTS methods, and try to how to find the minimum energy path. And for the kinetic isotope effect, we will use the cyanide molecule as an example. So you can try to find the transition state of the isomerization of cyanide and calculate the isotope, kinetic isotope effect. So what is now showing in the screen is a potential energy surface. From a computational point of view, many aspects of chemistry problems can be reduced to questions about the potential energy surface. So it's like a Haley landscape with valleys and like mountain paths and mountain peaks. Since we live in a 3-dimensional world, most of the potential energy surface you see are 3-dimensional, but the dimensionality of it is definitely much more than that. So formally, the dimensionality of the potential energy surface is the same as the number of geometric freedom of a molecule. That is 3n minus 6 and is the number of atoms. Why it's not 3n? Because the absolute coordinates or geometry, the position of the atom doesn't really matter. When we talk about molecular system, it's the relative position of the atoms matters. So that's why it's 3n minus 6 for a molecular system that has 3 or more than 3 atoms. And from the potential energy surface, when you see these values, that's the minimum. It can be reactant or product. We usually call these like values intermediate. And then through the mountain path, you would see this a saddle point. It's the like lowest point. Like in but it's the like highest point in the reaction path, and it would be the lowest point for any other path for any other dimensions, and that's what we call a transition state. And you would also be able to see the mountain peaks in a 3D potential energy surface, and that's the second order saddle point. And there are more than one reaction paths like that connects different minimums, different like intermediates. And each molecular geometry corresponds to a position on the potential energy path. And when you talk about energetics of a reaction, and that's the height difference of like these minimums, these intermediates. If you start from a valley that's higher than the other, then your Gibbs free energy change is negative, then that would be a spontaneous reaction. If you start from a lower valley and end up at a higher valley, then your Gibbs free energy is positive, then you get a non-spontaneous reaction. You would also be able to kind of tell the rate of the reaction by looking at the difference of the height difference of the transition state and the valleys. If this height is very large, that means you have a high barrier. The rate, the reaction is not going to proceed fast. If you have a very low barrier that's easy to overcome, then it's very likely that the reaction gonna happen very fast. When you calculate a vibrational spectrum, and that corresponds to the shape of the valley, if you get a very large frequency, that means it's a very steep valley. For different electronic state in in chemistry, that corresponds to like a different potential energy surface. Here we only show one surface. That means when you move like across different points on this surface, you stay at the same electronic state. There's no like electron transfer between the state. And when you talk about electronic spectrum, that's like the spectrum is actually the like separation between different surfaces, the gap between different surfaces, and that's like kind of the electronic spectrum. And for other molecular properties like dipole moments, polarizability, and then MR shielding, and they are basically the response of the energy to apply the electric or magnetic fields like for those points on this potential energy surface. So being able to map out the potential energy surface is very useful. But like since potential energy surface has a dimensionality of 3n minus 6, we won't be able to plot that in our real world easily. So most of the time, we would just use a slice of the potential energy surface. And that's with the x-axis as the reaction coordinate and the y-axis as the relative energy. A adiabatic potential energy surface is one in which a particular electronic state is followed. Yeah, that means there's no electron transfer between the states. So under adiabatic potential energy surface, the Born-Oppenheimer approximation is usually good. But if you have multiple surfaces that are very close and may cross with each other, that's a diadiabatic case. It's much more complicated. Yeah. So yeah, a slice of the potential energy surface would look like this. The x-axis, it's like what we call reaction coordinates. It's kind of a random coordinates. here we use the distance between the carbon and the hydrogen atom as the surface. So this is a reaction of the abstraction of the proton to to form a CH4. And the y-axis is just the relative energy. So for the potential energy surface, that's like more of a inner energy. But when we talk about reaction mechanisms, most of the time we need the Gibbs free energy. So to calculate the Gibbs free energy, the starting point is always the partition function. Inner energy, like as we have already mentioned in the morning session, or you might have learned this previously from the statistical mechanics. The inner energy is just a summation of all these terms, and then direct entropy that we get from all these terms, and the enthalpy, and finally we get the Gibbs free energy. For Gibbs free energy, that's not like you don't get a potential energy surface for the Gibbs free energy. Most of the time, it's just a energy profile. We just call it a energy profile. Here is a breakdown of like the inner energy and what are and it's like statistical mechanics expression of all these. The electronic energy is what you get directly from a for example, a Hartree-Fock or a DFT calculation, and then you want to add up the 0 point energy, which is the 0 temperature vibrational energy from the frequency calculation. Because when you do a frequency calculation, even at 0 temperature, you have like a half of HV. Like you've already have a part of vibrational energy, and the electronic energy plus this part gonna get you the 0 point energy. There's also a correction to the 0 point energy due to population of excited vibrational states, and they can be written in a sum of this. There are also contributions from rotation and translation. So with all these add up, that gives you the inner energy. With the inner energy, you would be able to use what we have talked previously to calculate the Gibbs free energy. So still, for the energies, the absolute energies are not accurate because we have so many approximations that's embedded in our methods to solve the Schrodinger equation. And relative energies have a cancellation of errors so that it would give you more accurate result. To calculate relative energies, you must use the same Hamiltonian, the same method and the basis set. For the enthalpy of the reaction, that's the product of the enthalpy minus the product of the reactant. And similarly, for Gibbs free energy, it's the of the reaction is the Gibbs free energy of the product minus the Gibbs free energy of a reactant. When you get negative, like Gibbs free energy of the reaction, that means the Gibbs free energy of your product is lower than the reactant. So you're going downhill. That's a spontaneous reaction. And when it's positive, you're going uphill. And that's a non-spontaneous reaction. And that tells the thermodynamics of a reaction. Oh, yeah, I've just gone through this part. Yeah, when you look at the potential energy surface, you get a slice of it that follows your reaction. If you get negative delta G, the reaction is spontaneous. It has a natural preference to become the product. But if it's positive, then the reaction is not spontaneous. But here, you only get the thermodynamics. A reaction that is spontaneous doesn't mean that the reaction is going to happen at your that at the speed that you can observe. So we also want to know the kinetics. I mean, if the barrier is very high, then it can hardly overcome the barrier and become the product. So even it's a spontaneous reaction, it might not necessarily happen. And that has to do with the chemical kinetics and the transition theory, because being able to find the transition state is essential for you to calculate the Gibbs free energy barrier. And being able to know the barrier would let you be able to know like the rate to predict how fast the reaction goes. And the transition state theory assumes that a reaction proceeds from one energy minimum to another through a intermediate maximum. When we say transition state, we refer to the configuration which divides the reactant and the product part of the surface on the potential energy surface. Well, the geometrical configuration of the energy maximum is called the transition structure. Like here, it's like the geometry of it. We say the transition structure. But under standard transition state theory, the transition state and the transition structure, these two terms, they are interchangeable. And we will just use TS to when we refer to the transition state. So the key point of today is how to find a transition state, because being able to find the transition state will give us a lot of information about the kinetics and how the reaction happens. But how to find a transition state? There are two general tips. One is to get close to the transition state. That means to the geometry that will look like the transient species. And the other is to get good guess for the transition mode, because we talked about calculate vibrational frequencies and predict the normal mode. And for transition state, you would have one imaginary frequency that corresponds to a certain movement, being able to predict the mode, like how the molecule vibrates, how the molecule rotates at the geometry, will also help you find the transition state. All right, now here we comes for our first hands-on part. In this hands-on part, I've already gave you a input file for a guess of the transition state structure. You would be able to visualize that transition state structure and submit a ORCA job to the queuing system. So this time we're not going to run it interactively. So what you need is to request a VNC session, and you want to copy the tutorial to your own Scratch directory. And the input file that I have provided you is called OPTTS UPS It's a open shell system, and you're going to use the command that I have provided to submit to the ORCA job. If you're not very familiar with the portal, I'll show you how to use the portal in a second. All right, here, if you go to the HPRC website, you would be able to find like a portal. We're going to use the GRACE portal, and you're going to request a VNC session. We're going to use to set 3 hours, use 2 cores, and they in fact we can use 1 core because we're not going to run the job interactively. We're going to submit to the queuing system. So I'll just have 8 gigabytes of memory and click launch. When the resource is available, you can click launch VNC session. In the meantime, we can go back to the portal, going to the files. So this is like a file browser on the portal. The tutorials for today can be downloaded from the Scratch trainings. Scratch training. There's the TS tutorial. We have a PDF, and which gives you the instruction for how to do the hands-on part. Like it has the instructions step by step. The first step is to ask you to connect to the portal and request the VNC session. We've already done that. And the next part, you want to copy the tutorials into your own Scratch directory. So here are like a few of the files that we're going to use. The first one is the OPTTS directory. You can view the input file using the file browser. So here, what we're going to do is to perform a transition state optimization with the EF algorithm. The transition state that we're looking for is the abstraction of a hydrogen atom from a methane to a OH radical. And you want to edit this input file yourself by following the instructions. For example, you need to type in the next line with exclamation mark UKS for unrestricted CONSHAM, like unrestricted EFT calculation, because the system that we're having is a doublet, has 1 unpaired electron. So it's we want to do an unrestricted calculation. And the most importantly, for a transition state optimization, you want to include the keyword OPTTS. And in the geometry input block, you want to add a calc underline has, because true. That means we're going to calculate the Hessing. Calculating Hessing helps the program to find the right transition state motion, to find the right movement at the transition state. So this is the coordinates of the transition state have already provided, like a gas structure of the transition state that have already provided for you. You can use a Modin or other program to take a look of what it looks like. Give me 1 second. Yeah, thanks, Chris, for posting the link to the GRACE portal. All right, when the session that you have requested is ready, hopefully this is large enough for everybody to see. And then you'll just want to copy the tutorials to your own Scratch directory. Mm. Oh, I think you need to have a to copy recursively with the dash capital R flag. Then you would then you should now see a TS tutorial directory in your own Scratch directory. Then you just go to the OPTS directory. You would be able to see these files. Well, I have a modem. I will open like using modem to try to open the input file so that you can see what the structure looks like. You don't have to follow me to do this step. Though I'm not quite sure if modem gonna open the input file. Well, unfortunately, it doesn't. But like the input file that we provided is something that's very similar to one of the slides that I've shown before. Give me just 1 second. If you remember, if you remember what, sorry, I don't think I've already gone through this. If you remember what this slide is, we're going to like find the transition state for this reaction. It's the abstraction of a hydrogen from the CH4 molecule. Like the OH group would take a hydrogen atom and form a water molecule and left a CH3 radical. So this is, and we're trying to find the transition state. So the structure that I provided you is like the coordinates of something that really likes this. It hasn't been optimized, so it's not like the highest energy point yet, but it's pretty close. Yeah, but all right, now let's go back to the setup. The OPTTS keyword in the input file will perform a transition state search calculation on the initial structure that like you provide. And this structure should be close to the geometry of the actual transition state. If it's not, then it won't be able to find the transition state. It will might continue to do the geometry optimization and find you the local minimum, like the bottom of the valley, rather than a saddle point. To include the keyword has, it's going to calculate the exact hashing at the beginning of the calculation. So it would have a better idea of which way to follow, which mode it's gonna try to follow. And so here I've already showed you how you're gonna modify the input file that I have provided you. And once you are done with this, then you can submit the calculation. Use the prepared job script that I have given you. And this task will pre-charge you 4 SUs, but it won't use all of the SUs. And when it's done, you can check make sure the calculation finished, terminated normally with the tail script. So if you go back here, like you can, if you know how to use VI, you can use VI. If not, you can go back to the file browser and try to find your ORCA, I think it's, TS tutorial, and the OPT TS UKS folder, and then add it. You would just modify it as what the instruction tells you to do. The keywords in ORCA, they're not case sensitive, so and once you finish the modification, don't forget to save it, and then you can go back to the terminal. You can cat the content of the file just to make sure your modification, you've done the modification. If you are good with it, then you can submit the job using the job script, which is just SBatch, and then I think it's do I have the job script here? Yes, I think I have the job script. So you just SBatch ch4 HOPTTS job. Sorry, my typo. OH. So what's inside the job script? So the job script allow you to run calculations in the queue rather than interactively, so that you don't have to wait there for your job to finish, especially if it's a large system and it will take a lot of time. So the HPRC has some primers to introduce you to the Slurm queuing system, but I'll just talk very briefly here. So it's the job script is a combination of the bash script and the SBatch, the Slurm script. The lines that starts with # SBatch has settings of how much computational resources you're going to request. We set the wall time to be 1 hour. If your job finished within 1 hour, then it will automatically exit from the queue. If it's still running when it hits the wall time, it will be killed. We're going to use 4 cores for this job, and it's going to use.
I'm sorry, your screen stopped sharing.
Oh, okay. Yep. All right. Sorry about that. I think my screen is not changing for a while. I'm just showing the content of the job file. This part just defines the computational resource that you just requested. And then the CD to Slurm submit directory changes the directory where the job was submitted from. You just call the ORCA module. For this hands-on part, we'll just use the ORCA 5 module. And then you just type ORCA and then input file, and then direct the output file to the output file. And that's what the job script looks like. Like you just use sbatch space with the name of the job file to submit the job to the queuing system. To check the status of your job, you can use sq-u with your net ID. Well, since this is for the Open On Demand portal, it's not my real job, because I've already I feel like it's a pretty short job. It's already finished. So this is my job ID. If I use Ceph with my job ID, you would say that it's completed. It's already exit from the queuing system. I got a lot of output files. So in these output files, I want to point out to the .out files. That's the general output in text format. The trajectory files is a file that has like multiple XYZ files that you can open it with either Modin or Avogadro. Like the XYZ file is the final optimized geometry. It should be the geometry of the transition state. The trajectory files is will show the intermediates during this optimization. The GBW file, this is a binary file, so that you won't be able to use a text editor to open it. And the Hessian files contains the Hessian matrix, which we might talk about in a we might use in a second. Make sure, you job terminate normally, and we're going to grab the frequencies just to check if what we get is a transition state. If you remember that for local minimum, all the frequencies should be real. And for a transition state, we're gonna have one imaginary frequency. So I'll just use the first. I want to check if my job terminates normally or not. I see it takes about less than 2 minutes, and I got all terminated normally. And next, I'm going to grab the part that has vibrational frequencies. I'll just, it won't be able to grab all the vibrational frequencies, but I think I have a typo. Frequency And from the result, you would see like the sixth mode is an imaginary frequency. By imaginary frequency, it puts a negative sign in front of it, and it says it's imaginary mode. So with the frequency calculation, we would be able to characterize, like we know that this structure has one imaginary frequency. It is a saddle point on the potential energy surface, but we still won't be able to know if this is the imaginary. This is really the transition state that connect the two minimum of that we want, because on the potential energy surface, there are a lot of different valleys, and they all can connect to each other some way. We need to visualize, to see the motion, to be able to have a better idea, like if it's the transition state for minimum A to minimum B, or if this is the transition state for minimum B to minimum C. To visualize the imaginary mode, we're going to like export the vibration and open it with a molecular visualizer. We're going to use Avogadro this moment, since our Avogadro is installed as a like in a singularity container. You need to use a BNC session to be able to use Avogadro on on this mission at the moment. So you just load the Avogadro module and open the XYZ file, which is like the you see like it's the sixth mode. We'll just be able to visualize that. So I'm going to load my Avogadro module. The name of the file is called so this is the hopefully the optimized geometry. And if we want to take a look at the imaginary mode, we'll check loop, and then we see the mode of at this transition state. So the transition state that we are looking for is the abstraction of a hydrogen atom from CH4. Does this kind of movement corresponds to the reaction that we're interested in? It is, because we see that the carbon hydrogen bond is stretching, and the hydrogen moves like between the carbon and the oxygen. So this is exactly the transition mode that we're looking for. If you get another, like you might get a different structure that also has only one imaginary mode, but the motion that you see is the stretching of the oxygen hydrogen bond, then you find the transition state, but that's not the transition state for the reaction that you're interested in. So yeah, this with this, I'm just to want to show you how you find a like transition state and how to and calculate the vibrational frequency and being able to visualize the mode so that you know you're finding a transition state for the particular reaction coordinate, because there could be many like transition state, many first order settle point on that big potential energy surface. Yep, that's about the first part of the hands-on. Please indicate in the chat if you're able to do this. And we will take a 5 minutes break and come back at 2:25. All right. Before the hands-on part, we briefly mentioned that the two general rules to find a transition state is to have a good guess for the geometry and a good guess for the motion. So how do you get a good guess for the geometry? One is by intuition, by like examining the structure of the reactant and the product carefully. You might have a good feeling of what the transient species, what an intermediate structure would look like, what a middle structure would look like. And for some other cases, you might get the inspiration from a literature if you're calculating a transition state that might has appeared from a system that with similar structure, then you might be able to take the structure of that transition state and make slight modifications to fit your need. If just guess a geometry from like out of nothing is somewhat too difficult, then the potential energy surface scan plus constraint minimization may help you find a better guess of the geometry through a more systematic way. For the constraint optimization, or what we call a relaxed surface scan, you can scan over one coordinate, or ORCA allows you to like set up a scan for multi-variables. And a third way to do this is to do it through a what they call a nudged elastic band, NEB. And to get a good guess for the transition mode, you can do that by calculate the Hessian. By default, the program will have an estimate of Hessian, but it's recommended that you calculate the exact Hessian at the start, at least at the start of the job, at the start of the TS optimization. Then it will, the program will have a better idea to find which mode it tries to follow. So for the TS optimization, the job type that we just tried, what you really need is just a structure that close to the settle point. That's almost all what you need for the TS optimization. And when you choose to calculate the exact Hessian, you would be able to see a part like this in the output file, the redundant internal coordinates. In the last column of the output, you would be able to see something called TS mode. the numbers here, it reflects the magnitude in the TS eigenvector. That means the fraction of this internal coordinate in the linear combination of the eigenvector of the TS mode. Like the larger this number is, the more like the internal coordinate that it corresponds to plays a more important role in this kind of mode. So here you would say that it's the distance between the oxygen and the hydrogen, because when we do the abstraction of the H atom from CH4, the product is a like OH radical. So of course, the distance of the oxygen and hydrogen changes a lot during this reaction, during this abstraction. So like it has a large like number here. That means we're looking for the right, like in the right direction. And the program will perform a transition state optimization using the eigenvalue following algorithm. And once the optimization is done, it will automatically perform a frequency calculation to check the like number of imaginary mode to make sure it is a transition state. But you don't have to wait until the optimization is done. You might want to take a look at the internal coordinate and the TS mode after a few cycles, like at the optimization, to make sure that it's going towards the right direction. If you see like the internal coordinate that has a larger number here is not the like the reaction that you are looking for, then you might want to like just stop the geometry optimization, because it's not going to the right direction, and you want to go back to guess a new structure as a input. When guessing is too hard, a relaxed surface scan is one way to find an approximate minimum energy path connecting two minima, and the saddle point is then located by an eigenvector following method. So with using the scan, what you need to provide is a starting structure. The starting structure does not always required to be optimized, but it would be better if it is a stable structure. I mean, it is a like optimized starting structure. And to be able to do a scan, what you need is you need to find a internal coordinate that resembles the real reaction coordinate sufficiently well. For example, here, like if you want to start with, say, H4 and a OH, the OH would take a hydrogen from this CH4. The coordinate that would change the most, like during this reaction, would be the distance between the carbon and oxygen, or the distance between, the carbon and hydrogen, and the distance between the oxygen and hydrogen. You can choose which coordinate you want to use, but for this one, I think it shows the distance between carbon and hydrogen. And for the scan direction, you always want to start from a more rigid structure to a more flexible structure. So I think though it graphed from left to right, but I think for this one, the scan was actually done from right to left. It starts from a CH3 and a water molecule, and then it scans the distance between the carbon and this hydrogen from 2.0 angstroms and shrink this distance until the carbon hydrogen distance becomes very small. So when you start from a more rigid structure, when you start from a more relaxed structure and scan towards to the more rigid structure, usually it's like the first part would be pretty smooth, and it would be easier than scanning from the opposite direction. Yeah, for the relaxed surface scan, it's just like a series of constraint geometry optimization at this point, at the point where the carbon hydrogen distance to be 2.0 to be at each of these distances. And once the scan is done, the program will automatically, or you pick the highest energy point and do a TS optimization as what we showed in the previous slides. And you take this structure as your guest structure for the transition state. For the notched elastic band method, we will use the example of the hydrolysis of methyl acetate into acetic acid and methanol as an example. When you do a NEB TS or NEBCI climate image, what you need is a optimized starting geometry and the optimized end geometry. Sometimes you would call this as reactant and product, but they are both intermediates in a more computational chemistry term. The starting geometry and geometry are need optimally. You want to use the optimized geometry for both the starting point and the end point. And what's more important is that the geometry should have their atoms in the same order. So it's like the program try to match the the corresponding atom to try to map the atoms in the product to the atoms in the reactant and find a kind of an intermediate, find a middle way. You can provide a gas transition state, but it's not always necessary. And what you can get from the NEB-TS calculation is the final transition state geometry. Like in the ORCA output file, it was saved as the NEB-TS converged XYZ. And you may get possible intermediates during the NEB. For example, if this is your starting point, even if it's optimized, but it and when once you've done the NEB, you find the transition state, but you might also find intermediates that more close to the, that are locally more close to the transition state. And these are the intermediates that you need to extract the geometry and redo the optimization. Because when you try to calculate the Gibbs free energy barrier, like the energy difference between the transition state and the intermediate it connects to is the real like Gibbs free energy for this, like for the reaction from this intermediate to this intermediate. So yeah, it's really cool that the NEBTS would like be able to find possible intermediates for you. And then the final trajectory from reactants to products, kind of like each of these points, it can be read from a trajectory file. All right, now it's time for the second hands-on session. In this hands-on, you will run a NEBTS calculation to find the transition state for the keto-enol tautomerization. So a keto enol, you want to do a geometry, if you start this from the beginning, then you might want to do a geometry optimization of the ketone first, and then you want to modify this molecule to get a structure looks like this. The reason that you don't start drawing a new structure is you want to keep the atom number to be the same. Well, you may not see this very clearly, but here the atom number for this carbon is 1. It should be also 1 here in the product. You see the hydrogen has a atom number to be 5 here, and when you see it in the product, this hydrogen also has the atom number 5. So the atom number of the product and your reactant has to be the same, or the program will have a difficult time mapping the product to the reactant. You can, but here for the sake of the time, I think I've already provided you the geometry of the ketone and enol. Make sure you just use Avogadro to check if the atom number matches for the product and the reactant. And then you're going to create an input file for the NEBTS calculation and submit it to the queuing system. All right, let's move back to the terminal. First, you want to go to the folder called keto enol, and then you want to use Avogadro to take a look at the geometry, and this is the content of the input file. We're going to use B3, it's a DFT calculation, and make sure you include the keyword NEBTS. And when it's done, you want to do a geometry, you want to do a frequency calculation following the transition state optimization, just to make sure it's a transition state with a imaginary mode that you're looking for. And the percent NEB, that's the NEB block. Here you're going to provide the geometry of the end structure using the XYZ format. And then if you have a gas geometry for the TS, for the transition state, you can also have it here. Since I don't have one, so I'll just comment to this line. And then we're going to use 24 cores for this job. And then the starting point is the structure of the keto. So let's do this. So I'm going to use Avogadro to take a look at the geometry. So now I'm opening the files for the Kiddo to be able to see the atom number. You might want to turn on the label and change the atom label to atom number. And you would be able to see that the hydrogens this carbon are like 3, 5, and 4. And when we use the like when one of the hydrogen transferred to the oxygen, make sure it's definitely one of these 3 hydrogens. Do I have a second field control? Now I'm opening the inno XYZ and I'll turn on the label as well. And I'll try to have the windows in a way so that we can see them at the same time. If I put these 2 geometry side by side, you would be able to see that like the carbons, they are atom 1 and 2 in both cases. And here it's this hydrogen, it's the 4th atom. Like except for this hydrogen number 4, all the rest of the atoms are like almost at where it was originally at. And yeah, so being able to have the same atom number is very important in this kind of NEBTS calculation. All right, now you can close Avogadro. And to create a input file for this calculation, you can either copy paste from the instruction, or I've already provided you a sample input file. I'll just and you can see what's in like the content of this file. So we're just yeah, I've already gone through what the input file is and what each of these command means. So we're just run the calculation. This job might take about 2 minutes to finish. So the status of the job is running. All right. I think we will take a break to 3. Yep. I think we will take a short break and we'll come back at 3 p.m. Okay, I think I said something wrong about the time it takes for the NEBTS calculation. I think for different of the climbing images, it can do different images in parallel. But for the most part, for the NEB part and the TS calculation, I think it's a single core job. So it takes mine has been running for over 10 minutes to now. But we'll just continue for the rest part and we'll check the results once it's finished. All right, so we talked about if we are able to know the transition state and the energy that corresponding to the transition state, we would be able to find the Gibbs free energy barrier. And with the transition state theory, we will be able to predict the rate constant from that. For the transition state theory and the Ewing equation and Arrhenius equation, they have different kind of expressions for the rate constant. For transition state theory, it used the Gibbs free energy. And for the Arrhenius equation, that's the activation energy. And it has a difference of the entropy. So be careful when you trying to make comparisons of these different expression. And for the kinetic isotope effect, like in a KIE experiment, a atom is replaced by its isotope, and it will cause a change in the rate of the reaction. The kinetic isotope effect are commonly measured using NMR to detect the isotope location, or a GC mass to detect the mass change with the replacement of the isotope. And the kinetic isotope effect can be used to determine the limiting step and the transition state. So for a example shown here, like they this can be formed either through the associative model or a dissociative model. If you're able to measure the KIE from the experiment to be around the 1.04, and you don't know if this if it's get to the product through a associative reaction model or if it's through a dissociative model, you can just try to predict the KIE with the computational model and calculate both the associated reaction and the dissociative pathway and compare the calculated KIE with the experimental one. For the associative mechanism, if your theoretical result is about 1.04, and if your calculated KIE for the dissociative method is only 1, then it would be more confident that what your reaction goes through the associative model. So that's kind of what the KIE can tell you about. So for the to predict the kinetic isotope effect, like why it's going to cause to make that difference. That's because when you replace with a atom with its isotope, the mass of that atom change. And the mass of that atom would affect the reduced mass of the whole system. And remember, when you're trying to calculate the vibrational mode, the vibrational frequencies, like it has the k over mu term. The mu is the reduced mass. The change of mass would affect this. And the change of the vibrational frequency would further down cause a change in the like energy, because there are energies associated with the vibrations. So it will cause a change in the 0 point energy. So that's how a change of a mass would would like affect your the energetics of your whole system. And to calculate the kinetic KIE, that's the rate constant of the light of this, like the system with the light element over the rate constant of the system that has the heavier element. And for like in the experiment, most of the time, the isotope substitution is from a hydrogen to a deuterium. And this is known as a deuterium effect. And that's why we usually just use KH over KD for the KIE. Normal KIEs for the deuterium effect are around 1 to 7. If you use the isotope of heavy atom, that means like a carbon, nitrogen, oxygen, sulfur, or bromine, then the isotope effect is much smaller, and it's usually between 1.02 and 1.10. And when you substitute numbers to this equation, make sure that you change the Gibbs free energy barrier to the unit of joule, because for the gas constant, this is the unit that we typically use for the gas constant. For the gas constant. So make sure that you cancel your units. All right, so the next hands-on part, you're going to use a relaxed potential energy scan to find the transition state structure and calculate the isotope effect for the isomerism of cyanide to CNH. Here, I'll provide you a table where that you need to fill out this space with the numbers that you got from the calculation. I've already provided you a sample spreadsheet in the tutorial, like in the Scratch directory that I've showed you. Here, like you need to find the Gibbs free energy for the HCN, the Gibbs free energy for the transition state, and calculate the free energy barrier from it's just the transition state, the difference between the transition state and the HCN, your reactant. Make sure convert this to joule per mole, because what you directly get from the output file is in atomic units, that is heart rate for the energy. And then you want to find out the rate constant using the equation that I just using formula that I provided in the previous slide, and then calculate the KIE for that. All right, let's move to the VNC session and see if the previous hands-on part finishes or not. I think I didn't yeah, resume screen sharing. Thanks. Yeah, give me 1 second to show you what I get from the ketone NEB calculation. All right, so once your calculation finished, you should be able to get a lot of files. Like it's gonna have a lot of image, like the NEB IM, because what the NEB does is that it use a like rough convergence or a more like relaxable convergence to like, because when it tried to map out the minimum energy path, I would first try to find structures that close to the path, but it might not be the minimum energy path, and then use a higher convergence criteria to find the real transition state. So let's see what we have in the tutorial. Once it's done, you want to use Avogadro to take a look at the minimum energy path. And then you can use Avogadro to take a look at the imaginary frequency. Okay. I still have Avogadro loaded, so I can just use Avogadro to take a look at the, I think I named my file differently, so that's why the name of the file gonna be different from yours. You might want to go to the extensions. Hopefully I'm able to drag my Avogadro window to where it should be. Not have just I just opened a new window because I couldn't drag my previous window. And you just go to, I guess if you go to animations, you would be able to see the like different trajectories that is it? Sorry, I think it's the minimum energy trajectory path, because I named my file I didn't name my files correctly. Sorry about the confusion. So what you get from the output file, like one of the files should be named as the base name, and then the minimum energy path, and then trajectory. Like that's the minimum energy path that you want to take a look at. And here, if you make it play it slowly, then you would be able to see that it's kind of changing from the kettle to the anode. All right, and to the optimized geometry for the transition state should be saved into a file just called NEB -TS converged XYZ. Like this is what the transition state would look like. And since we've already done a frequency calculation, we would be able to see the imaginary mode. There's only one imaginary mode that has an imaginary frequency of 2167. And we should be able to export this imaginary mode and then visualize with our Avogadro. I don't have ORCA loaded. That's why it doesn't do this. Oh, I think I've already export the imaginary mode, but I'll just do it again just as a demo. And 6 is the imaginary frequency. then I should be able to visualize it with Haragajo. So the motion that corresponds to the imaginary mode is the stretching of the OH. And you will see that the hydrogen number 4 approaches the carbon number 2. So it's like, or you would think it as like the oxygen takes the hydrogen from the carbon 2 away. Yep, and yeah, this imaginary mode is what is exactly what we're looking for. So so yeah, we're finding like the NEB method helps us find the transition state for the polymerization of keto to enol. If you want to take a look at the minimum energy path, like the geometry versus energy, you could do it through Modin. In like when you click the geometry button in Modin, you would be able to see that when you start from the keto, like this is the geometry that corresponds to it, and then the transition state is at the highest energy point, and then it maps to find the enol. Yep, and that's what we have for the second tutorial. And for the third tutorial, we're going to find the transition state with the scan TS. I have some instructions on how to set up the scan. It's just like a scan in the scan input block. If you're scanning along a bound distance, then it's like a B space with the atom number. If it's an angle, you need 3 atoms to define an angle and 4 atoms to define a dihedral. For the angle, you give your like start end. You start from 180 degree and end at 20 degree. You want to have 16 steps for the scan, so it will automatically calculate the step size for it. Oh, here, what you want to pay attention to is that ORCA label things start from 0. It label atoms from 0. So when you specify scan angle 3, 4, 5, it's actually your 4, 5, 6, your atom 4, 5, 6 in most of the visualization program. And with the scan TS keyword, it will do the scan, but when it finds the highest energy point, the scan, it will end the scan and optimize the transition state. If you still want it to do the full scan, then you have to add a full scan space 2, into the input file, or it will stop once it finds the transition state. Here for the HCM, you just want to have a starting structure for the HCM molecule, and we want to scan the angle from 180 degree to 20 degree. Here 210 corresponds to the HCN atom, and we're going to like scan 16 steps, each step with a degree of 10, and you just use the prepared job file that I have that you have in the tutorial, and submit the job. And when it's done, you should be able to get a optimized geometry for the transition state. And once you have the optimized geometry for the transition state, the next step you want to do is to run the thermochemistry calculation for deuterium, because the ultimate goal for this part is to calculate the kinetic isotope effect. You need to have the free energy correction for the deuterium version to be able to like calculate the rate constant for it. All right, so let's go back to the terminal. I'm not sure what happened to keto inol calculation, but for the HCM, I will just start from the beginning and see if I can do that or not. So I'm going to draw a HCN molecule to be able to do the scan. In order to get a good starting structure, I just want to do the auto optimization using the tool provided in Avogadro, and then save it to Oh, it just doesn't do it the way I would like it to do. But still, I would be able to create an input file. So I've already have one here, so I'll just use the one that I have already added. Yeah, it's like the scan has been set up, and the 0, 1, 2 corresponds to the like the HCN angle, and we'll just run it with the prepared job script. And once the job is finished, we're going to do the thermochemistry calculation for the deuterium version of that. But before doing that, we want to set up the input file for the thermal calculation. So I've also provide you a sample file. So we will take a quick look at that. The thermochemistry calculation, the input file of the thermochemistry calculation start with the exclamation mark with print thermochem. And then in the geometry block, you just provide it with a Hassen file. And then in the and the next part is the optimized geometry that corresponds to the optimized geometry of the transition state. Since we're going to use a deuterium to replace the hydrogen, here we just put the mass of the deuterium at the end of the line that has the hydrogen, and that's it for the input file. Oh, my keto inline job finally finished. And let's see how long it will take for the HCN scan this time. ORCA generates a lot of temporary files when the calculation is going. So it's highly recommended that you have a folder for each of your calculations. While you're waiting, you can calculate the find the optimized geometry for the HCN, like your reactant during this time. Similar as what happened before, like in the HCN scan, I've already provided you the sample input file for the geometry optimization of the HCN. Let's take a look on that. We'll just do a simple geometry optimization and frequency calculation to make sure it's a local minimum. And submit the job. Um, um, when the optimization of the HCM finishes, you should be able to find a Hessian file, and you can create a input file for thermal chemistry, which is a DC input here. And, this is a framework of the input file, which you're going to modify this by adding a few keywords to it. What you see here is just the X, Y, Z, the coordinates from the optimized structure of the HCN. And you're going to make a change to this input file by, for example, I think it's the print. I don't know. Give me 1 second. Then I'm having my thermal chemistry input file for the thermal chemistry calculation for the DCN ready. Since it's a pretty simple job. I'll just run it interactively. The output of the thermal calculation looks like this. Okay, since it's just a thermal chemistry calculation, like you don't have the electronic energy, you will be able to get the electronic energy from the HCN calculation. So let's see if, yeah, the calculation of the HCN finished. So we'll just grab the Gibbs free energy. From all the output files, the electronic energy from the HCN molecule is here. The Gibbs free energy for the HCN molecule is this number. For the DCN, you get the final Gibbs free energy correction by adding to the electronic energy. You get kind of the Gibbs free energy for the DCN molecule, so that you would be able to fill into the like table that I gave you in the slides. And for the transition state, once it's finished, you will be able to find the electronic energy and Gibbs free energy for the transition state from the HCN scan output. And then you can use your input thermal chemistry calculation input file to find the Gibbs free energy correction for the deuterium. And then use that number to like in the table. And then use the transition state theory to calculate the rate constant, then you would be able to find the KIE. The sample files that I included in the tutorial has a spreadsheet of this. It's not directly Give me 1 second to share my screen so you can see the content of the spreadsheet. So you need to fit, like once you filled in the table with these numbers, you will be able to calculate the KIE, which is about 3. Yep. Yeah, that's pretty much I want to talk about for today.